Hello, this is a re-record of lecture from Monday, October 23rd. So we started lecture off by talking about lithium, sodium. These elements share having one valence electron, so their Lewis dot diagram shows one valence electron. So our dot diagram is showing our valence electron count. So beryllium, magnesium share having two valence electrons, so we have two electrons being shown. So we could have written this Mg here or Mg here. I think this makes a little more sense because you're trying to show magnesium having a 3s2 outer configuration for the two valence electrons. Whereas the diagram here is kind of just getting us situated with having two electrons available for maybe bonding with other things. So maybe what we're going to picture is one electron going to a chlorine atom. So chlorine can make Cl minus, and then the other electron can go to another chlorine. So another chlorine atom can make chloride, and then we're making Mg2 plus in return by losing those two electrons. And so maybe the dot diagram showing the electrons, getting as far away as possible helps us picture some bonding events later. For boron, we see in aluminum that they share having three valence electrons. And so for boron and aluminum, we can see, let me zoom in a little bit, that they have a pair of electrons each. Now for boron, again, I'd probably think this is the more sensible dot diagram because I'm picturing maybe a 2s2, so maybe that's those two electrons, and then a 2p1. But when we draw boron this way, it's going to help us be able to see how hydrogen, where hydrogen's dot diagram, just one valence electron here. So hydrogen pairs up, makes one bond, two bond, and then three bonds with boron. And this turns out to be a stable compound for BH3. And we talked a little bit about how boron here sort of doesn't satisfy the usual octet rule, or it doesn't come up with a noble gas kind of electron surrounding it. But we'll talk about that as we continue. Carbon, we have four valence electrons. We have four dots around the atom. And again, we could have written this way, or this way is fine too. And so nitrogen, 2s2, 2p3, so we have five valence electrons. Oxygen, 2s2, 2p4, 6. Fluorine, 2s2, 2p7, so we have seven valence electrons here. And then our, kind of 8 for the octet rule is that noble gas configuration. And now what you can kind of see, it's not so much an octet rule as it's that completely filled shell of electrons. And so capping off the n equals 1 shell for hydrogen. So hydrogen would like to have two electrons surrounding it. It's just going to do so through forming a covalent bond, as opposed to things like NaCl, where we're going to get our noble gas configurations by sodium losing the electron, giving it away to something like chlorine to go to Cl minus. So we're going to see this on the next slide too. So we have ionic compounds form when we have metals of particularly low oxidation states and nonmetals of relatively negative and favorable electron affinities. And then we're going to share electrons like in BH3, like CH4 forming with carbon. That CH4 forms when we have hydrogen pair up here. So we're going to have the sharing of electrons when we have atoms that now are the type that have higher ionization energies and not as favorable electron affinities. So our ionic bonding, these are, typically involving metals with low ionization energies. If we recall, lithium, sodium, etc., have ionization energies of about 500 kJs per mole. Hydrogen's like 1300 kJs per mole to ionize the electron. So the I1 of hydrogen is 1300 kJs per mole. It's really hard to remove that electron from the H atom. So it's going to be easier for hydrogen to share its electron and keep a hold of it. So metals, low ionization energies, the nonmetals like chlorine, fluorine, etc., have favorable electron affinities. So these are going to be the case where it makes sense for sodium to lose an electron, go to sodium plus, chlorine to gain an electron, go to Cl minus, and then we're going to get the electrostatic attraction. If we remember, energy of electrostatic attraction or repulsion is kappa Q1, Q2 divided by D. And so as long as you have a negative and a positive, then our energy is of attraction. So the energy is negative in that case. So we get the attractive forces by bringing the two oppositely charged particles together. If we imagine doing a plus plus or a minus minus, then the energy goes up. And so we get the repulsion between two like charged particles. But plus and minus, once we form sodium plus Cl minus, we get the mutual beneficial attractive force. Now, something I was talking about in class today is that the ionization energy of sodium is about 496 kJs per mole. Let me erase this so that doesn't look like a negative sign because this is positive. In fact, let me write plus in. So about plus 496 kJs per mole. The electron affinity of chlorine is minus 349 kJs per mole. So you can kind of see here that we don't necessarily get any benefit, like the energy is still positive to remove the electron from sodium, give it to chlorine, but it's going to be that electrostatic attraction, that kappa Q1, Q2 divided by D. That's going to be the important term to consider because that's where we're going to then get some negative energy from the ions being attracted together once they're formed. So lattice energy is actually how we get that measure of attractive forces between particles. So if you look at sodium chloride, Na plus Cl minus, you have a mole of this compound. The energy that's required to completely separate 1 mole of the solid ionic compound into its gaseous ions, this is what we call the lattice energy. So lattice energy is how much energy it takes to break apart the bonds in NaCl and turn them into gaseous ions. And you can see that this is positive. It takes energy. So this is, of course, endothermic. Energy has to be added in to break this bond because the bond is stable. This is telling us that once you make Na plus and Cl minus, if we imagine making these ions here, and then they're, imagine they're gaseous ions, and we say, well, let's solidify these so they can experience their attractive forces, that this delta H here would be minus 788 kJs. So if we flip this reaction, we flip the sign, the key is that this is the beneficial term. This is why the ions form. So the ions form takes a little bit of energy to actually ionize sodium to sodium plus, chlorine to chlorine minus, but once we form them, we get this mutual attractive force forming between the ions. And then if you think, well, what happens when we put it into water? Topic for later, but water surrounds the ions, and we get the mutual attractive force between water and those ions, replacing these electrostatic forces of attraction. So we get a new force of attraction. We talk about that a little bit more later in chapter 11, but we call that the ion dipole force. Let's compare lattice energies for different types of ionic compounds. Again, lattice energy is the energy associated with the conversion of solid ionic compound into its gaseous ions. It gives us a measure of the ionic bond strength, so we can get a sense for compounds that have a greater lattice energy, they have to have a stronger ionic bond. And so let's look at the distance term. So if you imagine just in this equation here, we're dividing by distance. And so if I make the distance between the ions smaller, since I'm dividing by distance, then I'm going to make the energy of electrostatic attraction greater. And I'm thinking of the magnitude here. I'm thinking of the magnitude of the attraction of the ions. And that magnitude of the energy of attraction, this is just a way to make it a positive number, that this is directly proportional to the lattice energy. So if I make the attractive forces stronger, I make the lattice energy higher, of course. I make it harder to separate the compounds if the ions are more attracted together. So if I'm looking at NaCl, this is where we kind of started our discussion. If I imagine making the sodium atom smaller into lithium, lithium smaller than sodium, because it's higher up on the chart, notice that the lattice energy goes up. What if I make chloride fluoride, where fluoride's smaller than chloride? I make the lattice energy go up as well. So as my distance term is increasing, as my distance term, the separation of the ions is decreasing because the ions are becoming smaller. Like to scale, maybe lithium looks like this and fluoride looks like this. And maybe sodium plus looks like this and chloride looks like this, where they're just bigger. And so the separation is bigger in sodium chloride than it is in lithium fluoride. So smaller ions closer together, smaller D, greater energy of attractive force. So if you can have two charges that are identical, the closer you make them, the better. The harder it would be to separate those ions if they were closer together. And then you see the opposite trend emerge. If you go to potassium chloride, goes down, go to cesium iodide, really big ions here. The lattice energy is about 600 kJs per mole. But you can see here for the +1, -1 ions, pretty strong bond. I mean, if you remember covalent bond strengths from the end of chapter 5, covalent bond strengths for single bonds are about, maybe 200 to 500 kJs per mole. Double bonds, triple bonds, we're getting upwards into these ionic bond strengths for +1, -1 charged ions. Magnesium chloride, let's take a look at this here, so something we were talking about today for magnesium chloride, if you imagine this compound here turning into its gaseous ions, like magnesium 2 plus 2 chloride ions, that we're actually breaking two ionic bonds. So we have to break the bond between one MgCl minus and then the other MgCl minus. So if I break the bond in 1 mole of MgCl2, this molecule here contains two Mg2 plus Cl minus bonds. So when I look at my lattice energy, the lattice energy is the energy it takes to break both of them. It's 2526. That I'm probably thinking of dividing this by 2, and that's about, 12 to 1300 kJs per mole. Clearly a lot higher than the +1 -1s. But also, it's a lot higher just because there's two bonds being broken instead of just one. So the MgCl2, strontium chloride, now being smaller, a little bit lower. So we see the same size trend emerge that if you make 2 plus ion, the 2 plus ions smaller, you reduce the lattice energy. But the lattice energies of the 2 plus 2 minuses now the 2 plus -1 ions are going to be more stronger ionic bond for having higher charged ions. So if you look at the magnitudes of charge, now I like to talk about magnitudes of charge because, like, to me, a -2 charge is greater than a -1 charge because it's the magnitude of that charge. -2 charge would be greater. +2 charge is greater than a +1 charge. If I make the magnitudes of charge greater, I make the energy of attraction also greater. So +2 -1s, higher lattice energies. And then if I go +2 -2, that's even better. And so MgO only has one. We go back to having just 1 mole of the bond in MgO, and look at how much higher that lattice energy is. It's almost a factor of 4 higher than a comparably sized +1 -1 set of ions. And so for ranking these compounds in sort of order of increasing lattice energy, +2 -2s are greater in lattice energy than +2 -1s. Those are going to be greater in lattice energy than +1 -1s. And then lastly, scandium nitride. This is a -3, a +3. So look at how high that lattice energy is. It's almost a factor of 9 higher than a similar +1 -1 compound. Okay, so where do we actually get lattice energies from? We get them from something we call a Born-Haber cycle. Lattice energies cannot be directly measured in the lab, so we can't just blow apart an ionic compound into its gaseous ions and study that heat change in a calorimeter. So instead, let's use what we call a Born-Haber cycle. This is really just a fancy Hess's law cycle where we're going to add up a bunch of reactions and try to get to the desired reaction. So here we're given the first ionization energy of sodium is what its numerical value is. We're given an electron affinity. We're given some heat information for Na gas, Cl gas, and sodium chloride. And then we're asked to find the lattice energy of NaCl in kJs per mole. So the first thing I want to do is I want to write this reaction out that I'm going to try to take a bunch of reactions and have them add up to this one here. I'm going to try to have a bunch of reactions that sum up and cancel out to NaCl solid goes to sodium plus as a gas plus Cl minus as a gas. The delta H of this reaction is going to tell me something about the lattice energy of the compound because I have 1 mole of the compound here. So the delta H of this reaction is going to equal the lattice energy in kJs per mole. But we'll talk about this last step in a minute. And so what I might want to do is I might want to try to write out the reactions that go along with the first IE of sodium gas. So the I1 of sodium would be this reaction here, sodium as a gas going to sodium plus, still as a gas plus an electron. Now from chapter 6, chapter 7, where we're talking about ionization energies. From chapter 7, all the ionization energies were for gaseous atoms. Okay, we may have forgotten that or not realized, but all the ionization energies that we saw, all the electron affinities were for gaseous atoms undergoing those changes. And so this reaction here, the delta H, let me actually write delta H up here. So the delta H of this reaction here is just related to the ionization energy of sodium gas. So the delta H of this reaction would just be plus 496 kJs. It was kJs per mole, but I have 1 mole of sodium. If I want to write that out, the mole of sodium is just canceling. And so I'm going to go ahead and just leave that out to save the space. And then I'm going to write the electron affinity reaction for chlorine gas, plus an electron goes to Cl minus gas. And then the delta H of this reaction is given by the electron affinity. So this is where I use the electron affinity of chlorine. And then this reaction here would have a delta H of minus 349 kJs per mole times a mole, so just 349 kJs. And then the delta HF, so I can use these in a couple of different ways, this information. Like one place I can see is I want sodium chloride over here on the product side, but let me actually just write out the delta HF equation. Let me just write out that the delta HF of sodium chloride, that this value of minus 410.9 kJs per mole corresponds to the delta HF reaction, which is this one here. Now, how do I know this is the reaction that corresponds to forming sodium chloride? What I really mean by this being the formation reaction is that this is the reaction that's defined to have a delta H that's equal to the delta HF. So the delta HF here is minus 410.9 kJs per mole times 1 mole, so it's minus 410.9 kJs. And then the delta HF of sodium solid and Cl2, I have to know that those are 0. So sodium solid, 0, Cl2 is 0. And so if these are 0, then the delta H of this reaction is minus 410.9 kJs. What's kJs per mole, but times 1 mole of sodium chloride. Okay, so then let me write the delta HF for sodium gas. Let me actually leave some room here, because I'm going to end up flipping this reaction. I'll talk about why in a minute. But let me write this reaction out here, the delta HF of sodium gas. Well, that would be from sodium solid, the form of sodium with a 0 delta HF. So the delta H of this reaction would be plus 107.7. And then the Cl2, or excuse me, the Cl gas delta HF, I'm going to write that here. This will come from a half Cl2 gas. So this is just forming Cl gas as the product, 1 mole of it. So the delta H of this reaction is plus 121.7 kJs. Okay, so now if I imagine adding these reactions up, a lot of things are canceling, just not everything just yet. So the electrons are canceling. So the electron lost by sodium is gained by chlorine. And then a few other things cancel. But the one thing that's not canceling yet is the NaCl. So that's what I want to flip. I want to flip this reaction here. So I want to flip this reaction and write it as NaCl solid goes to Na solid plus a half Cl2. Because if I flip this reaction, I know that I just go to plus 410.9 kJs. So I just flip the sign of the delta H here. So I'm going to go ahead and just cancel this whole reaction out because I'm not actually using it. I flipped it. And so now let's go cancel everything out and make sure everything cancels. And so I already canceled out the electron. Sodium gas with a positive charge and chloride with a negative charge don't cancel. That's good because they're in the right spot. Sodium gas cancels sodium gas. Chlorine gas cancels chlorine gas. And then sodium solid cancels sodium solid. And then 1/2 Cl2 cancels 1/2 Cl2. And then NaCl solid isn't canceling, and that's good because that should be on the reactant side. And so then by applying the Hess's law, by adding these reactions up, all I need to do is add up all of these delta H's. So I go 496 minus 349 plus 410.9 plus 107.7 plus 121.7. And so what that gives me is that the delta H of the reaction is equal to plus 787 kJs. And then the lattice energy from the delta H is just that energy divided by 1 mole. So 787 kJs per mole, positive. Okay, so what this example is meant to show is where exactly we get lattice energies from is from a cycle of other delta H's that we can then study some other way. So you can study these other reactions in the lab and get their delta H's, and then accordingly from their delta H's, get the delta H here for this reaction. So this also shows the use of Hess's law from chapter 5. It combines some of the ionization equations from chapter 7. Okay, so which compound below has the greatest lattice energy? So the greatest lattice energy is going to be the smallest ions we're looking here. These are both +1 minuses. So being smaller is better for lithium fluoride. And then plus minus, and then +2 -2. So we have to be able to work out these charges because really seeing these charges is what's important. So MgS having greater magnitudes of charge makes it have a greater lattice energy. So more energy is required to separate the ions in magnesium sulfide than NaCl, and then more energy is required to separate the ions in LAF than cesium iodide. So let's get into the business of covalent bonding. So, maybe we're picturing something like H2. So maybe we have two hydrogens bonding together. And so each of these electrons here are being shared among the two atoms. So each atom has two electrons. Each atom kind of obtains that helium configuration. You have your negative electrons being attracted towards both nuclei at the same time. The nuclei do repel each other. The electrons repel each other. So there's going to be some ideal bond length for every type of bond that there is. So bonds can't get infinitely close. And then we'll see some more pictures of this as we get into chapter 9, but you can think of atomic orbitals in a similar way to what we looked at atomic orbitals. So we get some overlapping of, what look like s orbitals for hydrogen. So we get overlap where the greatest probability of finding the electrons is between the atoms. So the greatest probability coming from s orbitals overlapping, looking like this type of orbital here for something like hydrogen. So we'll talk more about orbital overlap when we get into chapter 9, when we talk about some different theories of bonding. So let's look at some different type of Lewis structures. So we see hydrogen forms what we call a single bond. So each hydrogen had one valence electron that then overlap and share through a single bond. Chlorine has 7 valence electrons each. So when we're looking at chlorine here, we're picturing starting with chlorine with 7 valence electrons. The other chlorine also has 7 valence electrons. And so if these chlorine atoms, if one of the electrons can't go to the other, like we're not going to do this, right? This would be kind of silly because why would one chlorine give its electron up to another when they both have the same desire for electrons, if you will, or the same nuclei? What if they share that electron instead across a covalent bond? And so that's how each of the chlorines ends up with 8 electrons, and the other chlorine ends up with 8 electrons. So they end up simultaneously satisfying their desire for that noble gas count of electrons. And so HF does this, so hydrogen fluoride also forms with a single bond. Water, oxygen has that 6 valence electrons, which pair up with hydrogen's 1 valence. So water forms a stable Lewis structure with 2 single bonds between hydrogen and oxygen has 2 lone pairs of electrons. Fluorine has 3 lone pairs of electrons. Nitrogen ends up with just 1, but it forms 3 bonds. So one of the things that we started talking about is the concept of formal charge. So formal charge is the net charge an atom bears in a molecule if we assume that we can break these like bonds in half. So if we assume 100% covalent bonds, that just means equally shared electrons, then can we calculate the charge of the atoms in the molecule? So nitrogen, just an ordinary nitrogen atom should look like this, which has 5 valence electrons. So if nitrogen has 5 valence electrons, its net charge is 0. So when I look at nitrogen in the box for ammonia, I see, should have 5 valence electrons, and it does have 5 valence electrons. So that means it has a neutral charge. So there's no charge in that nitrogen. Hydrogen should have 1 valence electron. It does have 1 valence electron. So all the hydrogens are 0. And that's good because if I sum up all the charges, just like the summing up all the oxidation numbers, I should get the charge of the molecule. If I sum up all of the formal charges, I should also get the charge of the molecule. So ammonia is uncharged. When I write the formula for NH3, there's no charge indicated, so it should be neutral, and it is neutral. CH4 is also neutral, and I see that carbon should have 4 valence electrons surrounding it, and it does. That looks like carbon's usual dot diagram. So carbon's charge is 4 minus 4 for 0. All the hydrogens are 0. Water should be 6 minus 6, so that's 0. Fluorine should have 7 valence electrons surrounding, and it does. That's a net uncharged fluorine atom. And so the diatomics, H2, 0 and 0, chlorine, 7 minus 7, 0 and 0. So you can see here, there's a pattern, and it's not always going to be the case that the atoms are uncharged, but in a lot of stable compounds, you're going to find that the atoms don't bear any net charges. Let's talk about, real quick, NH4+. So I talked about this in class at this point today. So we had NH4+. It had said, can we calculate the formal charge of nitrogen? So nitrogen here, this looks a lot like CH4. So if I break all these bonds perfectly in half, then what I have is I have 4 electrons closer to the nitrogens, 1 electron closer to the hydrogens, so the hydrogens are all 0. And then the nitrogen should have 5 electrons surrounding it, but I only have 4 here. So if I have nitrogen that looks like this, what would the charge of that nitrogen atom be? It would be positive because we've lost 1 electron from what nitrogen should look like. And so that's nitrogen with a +1, formal charge. So I might write a little plus sign here to indicate that formal charge. And now this is the formula for NH4+. So if I'm looking at NH4+ and saying, how many electrons should the Lewis structure show? It should show 5 for nitrogen, should show for the hydrogens 1 times 4, so 1 each times 4. And then because of the positive charge, I kick an electron off the valence structure, the valence orbitals of the molecule, so that gives me a total of 8 valence electrons. And so the Lewis structures are going to show us the valence electrons and what they're kind of doing as they're making these covalent bonds. And so, like, one of the keys is that if you're looking at a Lewis structure, we're trying to show you the valence electrons and what they're up to. We're not really concerned with the core electrons. What about O2 and N2? So O2, 6 times 2 should have 12 valence electrons. So if I imagine having oxygen looking like this oxygen looking like this, I'm going to pair up and make a double bond. So O2 is a double bond. And that's 12 electrons. So when I see 12 electrons, my proper Lewis structure should show 2, 4, 6, 8, 10, 12 electrons. N2 should have 10 electrons, 2 times 5. Nitrogen forms a triple bond. And so then notice that for oxygen, double bond gives each O 8 electrons, satisfying the octet rule, and also 0 formal charges. And then nitrogen here, let me rewrite the structure. Nitrogen, triple bond, nitrogen, lone pair. That if you imagine we break this bond here, also has a 0 formal charge. The other nitrogen, obviously the same for 0. And then also each nitrogen has 8 electrons closest towards itself. You count all the electrons for the lone pairs and the bonding pairs. So each nitrogen has 8 electrons surrounding it. So we're seeing for a lot of molecules, the octet rule is being satisfied. We have 8 electrons surrounding the atom. if you count all of the bonding pairs and the covalent bonds. But then if you break the bonds in half, you can then calculate this formal charge, which is the net charge an atom would bear if you imagine all the electrons being equally shared. Now let's come back to BH3 real quick. So for BH3, we had something that looked like this. And then for boron, should have 3 valence electrons surrounding it, and it still does. So boron's formal charge here is 3 minus 3 for 0. So BH3 exists. You can ship it in a gas cylinder, so it's stable enough to exist, to be shipped. Just kind of showing you that you can have a stable compound where we're actually violating the octet rule within the Lewis structure. So the Lewis structure shows an deficiency of the octet, so boron doesn't have a noble gas kind of electrons, but that's perfectly fine because it has the right balance of charge to allow it to have a 0 formal charge. So a couple other Lewis structures, so CO2, double bonds here between, let's actually be a little bit more careful here. So let's do this double bond here, and then we make this double bond here. So just kind of showing the electrons of carbon being used to make 2 double bonds. For CO2, this is just showing us nitrogen here, making the triple bond. And then this is showing us that if you imagine a triple bonds are generally shorter than double, which are shorter than single bonds. Now, I also was talking about how you have to maybe add hydrogens to get to these structures here. So let's show some extra lone pairs on our molecules, just that we can imagine like N2, shortest bond of the 3, NH2 or NH, a little bit longer of a bond because it's a double bond, and then NH2, the longest bonds of them all. So the bonding electrons kind of like act like a glue to hold the atoms together. The more bonding pairs of electrons there are, the more glue there is to hold the nuclei together, the shorter the bonds grow. That's going to be a theme that we see a lot throughout this chapter. And then one of the last topics for today is the topic of bond polarity. So bond polarity is the measure of how equally or unequally the electrons are shared in a bond. So if we imagine something like an F2 bond, that both the Fs are kind of trying to pull on the electron pairs, but they both pull equally strong, so neither fluorine ends up being polarized. See, the question is, does one nuclei pull this electron pair closer towards itself? Well, fluorine sets up a perfect tug of war. So it has 2 of these same nuclei pulling on the same pair of electrons. So the electron's negatively charged. They're being pulled equally as strong by both electrons. So neither atom can develop a charge. And then we would say the bond in F2 is a nonpolar bond. So a nonpolar covalent bond, the electrons are equally shared. We're not developing a charge separation. The atoms don't get, one of them a plus, the other one a minus, or some sort of charges associated with them in a nonpolar covalent bond. So this happens when the nuclei have a similar desire for electrons. Now, have a desire for electrons, this is going to be called electronegativity. So if the 2 nuclei in a bond have similar electronegativities, then neither atom becomes polarized. Neither atom develops a different charge than the other. And then what about a polar covalent bond? This is one where atoms in the bond attracts electrons towards itself with a greater force than the other nuclei. One example is hydrogen fluoride. If you look at this molecule here, we have this pair of electrons here. Now, fluorine is a different nuclei than hydrogen, and it has a much higher effective nuclear charge, if you recall from chapter 7. It's also pretty small. So having a positive charge and being small really allows it to pull those electron pairs more closely towards itself. Now, what this does to fluorine is it makes it partial negative and makes hydrogen partial positive. If fluorine were even stronger, or maybe hydrogen also didn't have some desire for the electron, then this may have gone all the way to this. So if it went all the way to this would be what we call 100% ionic. And so I just wanted us to show that if it made it all the way to -1 electron, then it would have been ionic. but it's going to be somewhere between a charge of 0, which would be 100% nonpolar, and it's going to be somewhere between 0 and -1. And then the hydrogen is going to be the opposite of that charge, but also partial. It's going to be somewhere between 0 and +1. And I mentioned this in class, and I'll mention it here, that the actual delta here for HF ends up being 0.44. So fluorine's negative 0.44 units of charge relative to that of an electron, and then hydrogen's plus 0.44 units of charge relative to an electron. And so meaning -1 and +1 would have been ionic, but it's somewhere between nonpolar and ionic. Some books, I don't think ours defines this as being, maybe somewhere in the homework problem, there's a homework problem that defines this as being about 44% ionic character. So it's like 44% ionized would be the idea. So we're getting some ionization, some developing a charge, but it's partial, not full negative. And it's about almost halfway. It's almost halfway to being ionic, if you think of it that way. And these partial negative charges are really important. This is going to lead to that hydrogen bonding force of attraction. We're going to see this in water as well. So a really important consequence of these partial charges is going to be an especially strong attraction between adjacent molecules that share those charges. And so nonpolar covalent bond for HF. Let's take a look at this slide here showing us for F2, equal sharing of electrons. This is perfectly nonpolar. LIF is plus minus. This is perfectly ionic. So it's about 100% ionized, meaning we have lithium plus and F minus. And HF is somewhere in the middle. So HF is somewhere in the middle of HF being partial negative, partial positive, and almost perfectly so. We'll be able to calculate numerically what this is based on something called a dipole moment, and then based on its bond length. We'll work on that calculation at the start of class on Wednesday. Before we get to that problem and before we wrap up, I just wanted to show the electronegativity chart. So electronegativity is increasing left to right towards fluorine and decreasing top to bottom. So it's highest for fluorine. So fluorine in bonds is the element with the greatest desire for electrons. It's trying as hard as it can to pull electron pairs towards itself. And so it does that in HF, goes negative. It does it in lithium fluoride, where it goes full negative, full positive for lithium fluoride. And it just isn't able to do so in F2 because it's the same atom pulling on the same pair of electrons. So we stay nonpolar for F2. And so the magnitude of difference, notice that our nonmetallic elements, the elements I just circled aren't exactly nonmetallic, they're metals, but they behave like nonmetals because they have a relatively medium desire for electrons. And then notice all the other nonmetals are somewhere north of about 2. So the difference between our nonmetals and also a few of these metallic yellow shaded elements have differences of electronegativity that are less than 2. So they're somewhere in this 1.5 to 1.9 range or lower, and that these are generally what we think of as being our polar covalent bonds. In particular, this sort of, I would say both these ranges here. As long as the difference isn't 0 or really small, we have some sort of polar covalent bond. And then we're getting into this difference here. This is, okay, I'm actually misusing this chart here. Let me back up a step. If we look at the difference of electronegativity of the atoms in the bond, so that would be taking the 4.0 minus 2.1 for hydrogen for about 1.9. If you're in about this range or lower, then that's where you're calling a bond to be polar covalent. So if you take any of the atoms shaded in red or yellow, paired up with an atom that's not itself of the same color, that same shading, then you're going to have one of these polar covalent bonds, or even a non-polar bonds if the electronegativities happen to be the same. Like N and Cl, it's kind of a tricky question of like something like NCl3, where the electronegativities of N and Cl are about the same. It's not very polar. I mean, you could probably call it non-polar. That would probably be the best answer based on the electronegativity differences being exactly the same. But the bonds that have the exact same electronegativity and therefore have no charge would be the heteronuclear diatomics, like H2, F2, etc. That these ones here share that property of being exactly and perfectly nonpolar. So we get nonpolar when the difference is small between the electronegativities of the atom. But notice NOFCl, they're shaded in red because those are the four most electronegative atoms. You pair those up with just about anything, then the bond's going to be polar. And the only weird, one that maybe wouldn't be polar is the NCl bond itself. But you take something electronegative, pair it up with something that's not, then you're going to have a polar bond. And I think this is the last problem that we looked at in class today. So we were looking at the difference of electronegativities between NO, NF, F2, and then the NCl. And so because fluorine's the highest electronegativity here, nitrogen's the lowest, the NF bond has to be the greatest have the greatest polarity. That means the N atoms and the F atoms we would expect to have developed in a compound like NF3. If you have a compound that contains these atoms, you expect the magnitudes of charge in NF3 to be greater than those charges in, say, NCl3, because the atoms the bonds aren't as polarized. And so then the NO bond is just not as polarized. The difference isn't as great. So we wouldn't expect the charges of the atoms in an NO bond to be as great as something like an NF3 bond. So NF3, we're going to see Lewis structures later. This is going to look something like this, where we have three of those NF bonds. And then F2 would be the lowest, because this will be exactly 0. So this one here would be the lowest. And then probably NCl, maybe you would say NCl also should be low because its difference works out to be perfectly 0. But two of the same atoms is really great because the electronegativity difference has to be equal to 0. Okay, so I was just advancing to the final slide. I didn't talk about this slide in class today, so this will be our stopping point for this video. So apologies that this was a little bit late getting posted today. I had to re-record, but hopefully this video reaches whoever needs to see it, and you can receive this information. Today I was actually on the chalkboard due to, forgetting my iPad. So here I am re-recording the video, but hopefully this second pass through the lecture for me today, and then if you get a chance to watch this, helps gain some insights into the first kind of few sections here into Chapter 8. And we'll be spending Wednesday and Friday getting into more types of discussions of mostly covalent bonding for the rest of Chapter 8, and then also into various types of Lewis structures for different types of compounds. All right, thanks for the attention.